My name is Aaron Bouget. I'm a research specialist here at Biosphere 2. I've also been helping out with a lot of digital outreach lately, whether it be videos or webinars, and we're actually getting ready to roll out another podcast from the Biosphere 2 podcast. So keep an eye out for that as well. But it's my pleasure to introduce to you guys today three really incredible panelists that together bring forth expertise in disciplines ranging from oceanography, marine biology, paleoclimate, and coral reef restoration. So I'm going to introduce those panelists for you guys right now. Starting with Dr. Joellen Russell. Joellen is a professor of Biogeochemical Dynamics in the Department of Geosciences at the University of Arizona. Before relocating to Tucson, Joellen worked at NOAA's Geophysical Fluid Dynamics Laboratory during the intensive preparations for the Intergovernmental Panel on Climate Change, their fourth assessment. She currently serves as lead of the modeling component of the Southern Ocean Carbon and Climate Observations and Modeling Project, known as SOCOM. Welcome, Joellen.
Thank you.
Dr. Diane Thompson. Diane Thompson is an assistant professor of paleoecology, paleoclimatology, and marine ecology. She combines these disciplines also in the Department of Geosciences at the University of Arizona, and the director of marine research here at Biosphere 2, which is where I'm at behind me. We're in the ocean biome today. Diane's passion for the ocean started during childhood snorkeling trips to Buck Island in the US Virgin Islands. Prior to relocating to Tucson, Diane was awarded a 2-year fellowship at the National Center for Atmospheric Research. Her research bridges the fields of ecology, paleoecology, and paleoclimatology to investigate climates and reef systems of the past, and in turn, improve our ability to preserve reef resilience under current and future climate change. Welcome, Diane. And Dr. Joanie Kleypas. Joanie Kleypas is a marine ecologist with the National Center for Atmospheric Research's Integrated Science Program. She investigates how rising atmospheric carbon dioxide affects marine ecosystems and specializes in the global condition of coral reefs. She was one of the first scientists to illustrate the potential impacts of ocean acidification on marine calcifiers and has been heavily involved in the topic since 1998. She has served on multiple national and international committees related to ocean acidification and was a contributing author on that topic in the IPCC's 5th assessment. Welcome, Joanie. So you guys certainly produce quite a mouthful in terms of accolades and background in terms of introductions, but I want to give you a chance to speak for yourselves. And to our participants, I've asked our panelists to deliver a 2 to 3 minute opening remark. One that sets the context for their research and their background in oceanography here for World Oceans Day. But secondly, I asked them to deliver us a bit of a State of the Union like State of the Oceans address, a concise address that states the changes that they're seeing in the oceans from their background. So without further ado, why don't we start with Joellen and move down to Diane and Joanie afterward. Thank you, guys.
Well, I am thrilled to be here on World Oceans Day, particularly with 2 of my ocean science sisters here who are just extraordinary human beings. We're so lucky to have them. Diane in particular is in my department, and she is our ocean superstar, who is just doing extraordinary things. And of course, I've been a huge fan of Joanie for, most of my academic career, so I can't even tell you what a thrill it is to be here. And of course, looking at our beautiful B2 there behind Aaron, which is such an icon of how we look at the microcosm to stretch to our global ocean. And what is happening in our global ocean? So I'm not sure everybody understands just how much of global warming is ocean warming. 93%, 9 out of 10 of all of the heat that's being trapped in the Earth system due to CO2 increases. And of course, we just hit another record according to measurements over at the Scripps Pier. We're up over 417 parts per million Yeah, even under the pandemic, we are still breaking records in CO2. And what it does is it's basically warming the whole planet. But 9 out of 10, 93% is in the ocean. Only 3% in the atmosphere, 3% melting some ice, and 3% warming the Earth's surface. It's really 92%. And it's not just the heat. It's also, see, I study the Southern Ocean. I brought my ocean with me today. And that ocean, the ocean I study most of the time is the Southern Ocean around Antarctica. I bet you didn't know that 1 out of 8 molecules of carbon that comes out of anybody's tailpipe anywhere in the world, 1 out of 8 goes in around Antarctica. 1 out of 4 goes into the ocean, period. But 1 out of 8 goes in right around Antarctica. Those wild waves you're looking at on your screen, that's how it happens. So the ocean is doing this incredible heavy lift for us. And that heat is raising sea levels, destroying corals, that ocean acidification. We've already seen mass death of pteropods around Antarctica. These are huge, world-changing, ongoing impacts. And it's things I study with robot floats, supercomputers, and satellites, unlike my colleagues here who get wet. I've spent about a year of my life at sea, but my students are now the ones that are going to sea and deploying our robot floats. But that's how we're looking at it from the large perspective. And I think Diane and Joanie are going to tell us how we're seeing it in high definition, right up close. So, Diane.
Joellen, and I just want to reiterate that it's a pleasure for me to be here with 2 of my mentors and idols for many years. And as Aaron alluded to, I kind of have a unique background and wear a lot of different hats as both an ecologist and a climate scientist. I'm bridging these 2 fields. So I kind of have a unique path to get here. Growing up in the Midwest in Minnesota, I was fortunate to get to snorkel at a pretty young age. And I returned to the reefs that I fell in love with and had this picture of the corals that I had seen all those years back. And for the first time in my life as an undergraduate, I experienced devastating loss of a coral reef that I loved. So I kind of changed gears, and I joke I switched over to the dark side. I became a geoscientist, and I started using corals instead of monitoring them and trying to understand how to protect local reefs, how we could really tackle the elephant on the reef, if you will. That is the patterns and the pace of ocean warming. So now actually much of what my group does is we use corals, both living and fossil corals that grow all over the tropical oceans. And much like rings of a tree or a history book in the library, we can use these corals to really understand how our oceans have changed and how that pace may or may not be changing with climate change. So our team works all over the world, but specifically in the world's largest ocean basin and hotspot of biodiversity, the Pacific. And we're trying to understand these patterns of warming. And what we've learned is that tropical oceans are warming, and in many cases at an unprecedented rate. And we're also learning that these extremes are becoming more frequent and severe in many cases. But I'm here, and I switched over to the job here at the Biosphere 2 a couple years ago because I think there's incredible reason for hope. We've learned from this work that corals in certain areas are less likely to be susceptible to these types of stressors when they've been hit hard in the past. I've cored through these giant coral colonies and seen them die and then regrow. But we know from this work that we need to help the corals. The corals are resilient creatures, but they cannot keep pace without our help. So my State of the Union is together we must tackle that elephant on the reef head on by reducing our carbon footprint to ensure that we have coral reefs and all of the services they provide for generations to come.
Thank you,
Wow. It's going to be hard to follow these two women who I obviously admire. Joellen has worked a lot with a lot of the climate modelers that work at my institution, and she is highly respected. And Diane worked with me as a postdoc. And, you know, we have all of our mentors, and it's amazing to me how many of my mentors are people that I am supervising. So that is we learned a lot together in some projects that she did with us at NCAR, and I wish she, you know, I really hope that we can continue working together on all these problems, because in many ways we still do, just in different places now. My story is interesting. I'm the oldest one. I can give kind of a historical perspective, because when I was growing up, you know, I'm 62 years old right now. When I was growing up, I grew up in a refinery town, Port Arthur, Texas. And so what's really interesting about that is that, you know, you have this juxtaposition of really very polluting refineries, which, you know, my father raised 7 kids working at a refinery. And, you know, you're aware of the pollution, but you're also aware that it's your livelihood. And, you know, when I went to school at a local university called Lamar University around there, you also learned from my professors for the first time just how important the environment was. I had great mentors there, but no one was talking about climate change. I mean, I became keenly aware of environmental problems, particularly in the marine environment, because I was studying marine biology and oceanography there. Really impressive people at the time that had the vision to sort of imprint on me how important all this stuff was. I also went on after, you know, for my master's, I worked on fish. I got really involved with fish and understood just how intelligent they are and their behaviors and how rich the ocean was. It's like every time you move and you see another marine environment, you know, your world grows, and it's just becomes more impressive how incredibly diverse the ocean is. I mean, we think about our land and terrestrial systems, but when you get underwater, it's every bit as complex as rainforest and you know, what we think of as being, you know, our intelligent life. There's just as much intelligent life under the ocean. So you become more and more sucked into this. And on World Oceans Day, you know, I think this is what we talk about, the oceans, but it's the ocean life that makes us so incredibly different from all of the other places in the solar system that we can think of. I mean, we are a blue planet for a very good reason, and that's our oceans. I also had the incredible opportunity to work at James Cook University in Australia, and I got to work on the Great Barrier Reef. So that, of course, that blows you away even more. And that was before bleaching was a problem. We were trying to work on, you know, sort of what controlled where reefs grew. You know, how can we explain where reefs grow? And then later on, when I came back to the United States and started working at the National Center for Atmospheric Research, I was able to apply modeling to do that. But modeling at the time and climate, you know, was still not quite on the radar. We knew climate change was potentially a problem, but to be honest, this was in the mid-90s. A lot of the scientists there were really on the fence about whether it was a problem or not. But in 97, 98, when we lost 15% of the world's coral reefs due to a big El Nino event and big coral bleaching event, I think that convinced not just me, but a lot of my colleagues that this was highly unusual and very likely a consequence of ocean warming. So now it's sort of a given that we have these problems. We have the problems of ocean warming, we have the problems of ocean acidification, we have problems of ocean deoxygenation. It's kind of a 3 whammy thing that we've also seen in the paleo record during these big extinction events. So we're kind of frightened about this stuff, but I agree with both Joellen and Diane. You know, we have to stay optimistic about this. We know what's happening, we know how to reduce it. And I also want to say we're seeing incredible change right now through these marches, right, for social change. We can make social change happen. And so I don't want to be really, you know, depressed about all of these things that are going on. The only way we're going to find solutions is that we look at them and we stick together and we try to find them. So, so what I've started to do with my research is I use modeling techniques to
look for those places, like what Diane is finding, where these coral reefs can come back. Where are they highly resilient? You know, what makes them special, where they're going to be our refugia in the future? And then I've also started a coral reef restoration program in Costa Rica, which has been incredibly rewarding, as much for the fact that the corals want to grow. You just give them a little bit of hope and those corals feel it and they grow like crazy. And you can, you know, we can do a lot with restoration, but you know, it's a game where we're trying to keep up with climate change because they continually have to adapt to that. So I've actually written down my State of the Union for the oceans. And I basically said, you know, without a doubt, what makes our planet Earth unique is our ocean. But now our ocean waters are changing too fast for ocean life to adapt. And to reverse that trend, we must change the current situation where humans think of themselves as bad for the ocean to the vision where humans are good for the ocean. And if we can make that mental shift, then all of the things we need to do will follow. So happy Oceans Day, everybody. And we look forward to your questions. Thank you. Thank you, Erin.
Yeah, thank you guys. I mean, it really sets the context for our discussion. And it seems as though the three of you have all have dabbled in climate modeling in one way or the other. So I want to start with this animation. And just, you know, when I first saw this, I said, okay, satellites are getting really good. But I found out later that this actually isn't a satellite image, that this is a climate model. And I mean, one of the first takeaways that I had was just how much mixing there is going on, both in the atmosphere, but in the ocean as well. Mm-hmm. And when I think of the ocean, I think of this, you know, this vast, you know, sea. But I don't necessarily really meditate on just how much mixing is going on. And I think I'll start with Joellen and ask, so, you know, when we have carbon emissions that go into the atmosphere, how fast does that mix? And similarly in the ocean, how fast is warming mixing in the ocean? How fast is carbon mixing in the ocean? And I know that you've studied this quite extensively, so let's start there.
This is FV3. And I just want to point out to everybody that this is the core of an Earth system model that has been now passed from the Geophysical Fluid Dynamics Laboratory at NOAA, which is research at NOAA, to the Weather Service, which is now operational. So when climate and climate models sort of started converging, I said, oh, maybe the weather models will get so good that we'll use them for climate. That's not what happened. Because the ocean is so critical, weather models are basically atmospheric models. They have other components, or they can, but they're not designed for that. Climate models and Earth system models were designed for that. And this is an Earth system model. And they have passed the core of the atmosphere over to the Weather Service because the ocean is so important that we now need to know the temperature everywhere in the ocean in order to be able to do our forecasts. So if you like your new forecast, since September, it's been a climate model. Thank an oceanographer. Quite seriously, the ocean is why we have better forecasts. And it's the Argo array of floats, those robot floats, that are actually giving us the information, not just of the sea surface temperature, which are incredible satellites tell us about the sea surface temperature, but the content of the heat. How deep is that warm water layer? Because of course, you drive a hurricane across it, the size of the hurricane will depend not just on that the sea surface temperature, but how much heat is underneath it available. So this is a big deal. So atmospheric carbon, anywhere you emit it, like I said, 1 out of 8 goes into the Southern Ocean. Just so you understand, the entire world atmosphere is well mixed within 1 year. If you emit something up in Barrow, it will be well mixed with something at the South Pole within 1 year. No, really, seriously. So everywhere there is now an increase in the atmospheric CO2 every year. We have a little jiggy-jaggy on the Northern Hemisphere because of the trees making all of their leaves out of carbon. and then fixing it into leaves. And then when they die and rot or we burn them, et cetera, then they go back into the atmosphere. So you have a little dip, but basically all that CO2 is well mixed in the atmosphere and is pressing into the ocean. And where the ocean takes up the most tends to be where we have the most mixing. And and the reason is because that water may not have seen our human atmosphere. So the water coming up around the Southern Ocean and Antarctica may be 400 to 600 years old at a time. Not all of it, but a big chunk of it, because it's upwelling from very, very deep. So it hasn't seen. So 400 years ago, our CO2 looked like what we call the pre-industrial, before all the carbon, right? 1860s when we start most of our modern simulations. Seriously, this is how it works. And it's such an extraordinary thing that we are on this fully connected planet. The ocean affects us here in Tucson, not just in our monsoon season, but in our westerlies in the winter. Not just how hot it gets in the summer, but how cool it gets in the winter. All of this is being modulated. How long is our summer cabin fever season? I have 2 small kids. And honestly, if we're already at 1700 degree days now, right now. This is not normal for Tucson. 1700 degree days before the solstice is really nuts. So I'll just say, if cabin fever season gets any longer plus pandemic, honestly, mommy's gonna have to drink more. No, just kidding, just kidding.
Can I add something to that? Because I thought that was a really great way of describing how the atmosphere and the ocean are so interactive. I think what people don't believe, we always talk about how deep the ocean is, how vast the planet is. But the atmosphere, the bulk of the atmosphere is really only about 10 kilometers thick. That sounds like a lot, but we run 10Ks all the time. I don't, but my friends do, right? And the ocean is even less than that. So, we're talking about really thin layers. And so, of course, they're interacting. But they are also, even though they seem vast to us as small animals living on the planet, they're really rather fragile when you think about it. If you took all the water off the planet, there's this great image of the geology of the planet. You could just see just how thin the ocean is. But they do interact incredibly. So we have to know the ocean to understand how the planet operates at all, which is just how Joellen described it.
The ocean has 38,000 petagrams of carbon, and our atmosphere is somewhere, but usually has gone 600 to 900. We're really looking at a tiny fraction of the carbon is in the atmosphere. The rest is in, most of the available is in the ocean. So this exchange is really important. On the other hand, too, 92% of the heat, of the excess heat, is in the ocean. Only 3% is actually warming our atmosphere. So when I talk about that seasonal change or cabin fever, I'm really talking about, what did my ocean let me have this year? Because that's what's deciding the transient, what they call in technical jargon terms, the transient climate sensitivity, the now change, instead of the way out 1,000 years, but the now change is incredibly coupled to that ocean. And so what I worry about is what does happen to the biodiversity in our ocean? Where are the refugia, those last best places? And how soon can we bend the curve so that there are more of them?
Great.
Now,
maybe Diane could take it.
Yeah, I do
Yeah.
want to steer towards Diane, and perhaps in the midst of this, we had a question, what are some of the causes of ocean warming? And we've been talking about that, but we haven't set the function of actually how our oceans do warm. So Diane, maybe you'd be willing to speak to that, but I'd also like to ask you about some of your research with both wind and El Nino events. And Joellen put it interestingly, where the ocean is giving out this heat or these events to us. It's not necessarily every year. There seem to be some patterns with when oceans give us extra heat. And maybe you could speak to that in the context of El Nino.
Yeah, absolutely. So as Joellen said, the oceans are really covering us, if you will. They are taking up a tremendous amount of heat, over 90%. But how much exactly they take up every year really depends on what the climate system is doing. And so if you look at what the global warming sort of pattern looks like, it doesn't just look like a straight line. You'll see it looks a little bit like a stair step, where we have, periods where the Earth's atmosphere, so what's left after the ocean takes up that heat, like Joellen was saying, is really rapid. So it's accelerated warming. But then we'll have a decade, like in the mid 20th century and then the early 2000s, where the rate of warming, what we feel on the surface of the Earth, is much less. And it turns out that what's happening is that it's this trade-off between how much of the heat in our climate system and our entire Earth system is in the ocean and how much of it is what we're feeling in the atmosphere. And what we've learned is that winds, especially over this giant ocean basin that we're staring at right here, the Pacific, how the winds are pumping heat down into that giant reservoir in the ocean. It turns out when winds are really strong in the Pacific that we get much more ocean warming and much less atmospheric warming, and vice versa. And so now we really need to understand how and why winds are changing in the Pacific, which has been studied thanks to particularly buoys that have been put across the tropical Pacific since the 90s. And we've learned a ton about these winds. But we really need to go further back in time to understand over periods of tens to hundreds of years how winds really play this sort of regulatory role in our climate system. So that's work that we're doing in my lab. And it turns out that we can use information trapped in coral skeletons and islands in the middle of this beautiful Pacific basin to tell us about what winds are doing in the past and how we might use that, harness that information to understand these patterns and pacing of warming in the atmosphere.
Thank you, Diane. Joellen, I want to come back to you briefly because you mentioned your Argo floats. And from what I understand with your research, you're actually working towards building the most robust carbon verification system for the globe. Whereas if you add enough of these floats to the ocean, and these floats are helping create, incredible climate models like this, you're actually going to start to turn some of the responsibility for what's causing this warming back on the producers in the locale of where some of these greenhouse gases, which is one of the things that drives global warming, you're going to be able to start blowing the whistle a little bit.
We love transparent research. We love to just let it all hang out, right? Would you like my code? You can have it. In fact, it's available online. Do you want my data? It's all available online immediately within 2 hours of one of our floats popping up to the surface. They beam all that amazing pH, nitrate, oxygen, temperature, salinity data back by Iridium satellite, and with just a algorithmic quality control, we put it up online immediately within 2 hours. It's just automated. Up it goes. And we're trying to get it on the GTS, the Global Telecommunication Service, so that it would be available for weather forecasting as well. Because wouldn't we like an ecosystem prediction as well as a weather prediction? I mean, really, here we come. But in a longer sense, what we're doing is, so I had this epiphany as an oceanographer. Okay. So the uncertainties in the atmosphere are we have a great network, a global network of atmospheric CO2 sensors that give us incredible information about the atmosphere. And remember, it's well mixed within a year. Now the ocean takes a lot longer to mix the whole thing, and it's 72% of the Earth's surface, right? Okay, now I thought about that. I'm like, wait a minute. You mean the entire human problem of CO2 emissions is on that other 28%? Yeah. It's just the land where we live that is the major issue with carbon. The ocean is not actually, the ocean is mostly a sink with some exceptions that are really important, but mostly a sink for CO2. So what we did was we said, okay, we know the atmosphere really well. If we knew the ocean really well, that would only leave the land, which is only 28% of your surface. And if we just took the top 10 economies, the US, Canada, Russia, the EU, China, India, Brazil, you know, top 10 are really big contiguous areas, right? Indonesia, Australia, these are actually things we could do. So what we have out 200 floats in the Southern Ocean. We've been funded for another 200 over the next 5 years. And there is a rumor that this proposal, it's just a rumor, that the proposal was put in by my colleagues on SOCOM for an initial 500 floats to do the world. That's what we need. We will have, within the next 2 to 3 years, if all goes well, 800 floats worldwide. With a little help from our friends internationally, we will have a global network that is able to monitor carbon fluxes, carbon inventories for the world ocean. We don't have that right now. We have to do most of our work from ships, and there just aren't enough of them. Since 1989 and the end of the Cold War, the US at least, and most of Europe has been mothballing research ships and not replacing them. So it gets harder and harder for us to get out to do our work. So the robot floats are not, they are our backup. The ship was supposed to be our tip of the spear tool, but we don't have enough of them, and the change is too big and too fast to capture it all. So satellites and robot floats with supercomputers to do this incredible modeling, because in fact, we do want to say, so what we'd like to do, the goal here is every month we want to announce, you know how your Nest gives you a report? Anybody have one of these Nest thermometers for their houses? It gives you a report every month and it says, you get 3 green leaves. You made your schedule more efficient. Good for you. Sometimes it says you get 4 black leaves because you turned the AC up. Yeah. So what we want to do is do that basically for the top 10 economies. You get 3 green leaves. I'm so impressed with you. The United States has cut their emission 17% in the last 10 years. We had our peak emissions were back in 2007, and we're dropping almost every year now. We could do more if we were motivated, say, to beat Europe, to beat India, to, you know, wouldn't it be great if we knew where we sat and could work on our contributions with a top-down verification system based on our incredible ocean? That's the plan.
Well, I want to dive into the ocean now. Not that we haven't been in this fluid whirlpool of atmosphere and waves, but we have a question from Robert C. Robert asks, on land, the transition between ecosystems and biomes is named an ecotone. With climate change, these ecotones are shifting at a fast pace. In the oceans, are there similar transition zones that are exhibiting shifting, such as krill distributions or distributions of fish and other kind of ecosystems, whether it be kelp or coral? So perhaps Diane and Joanie could pitch in on this question from Robert. Thank you, Robert. Joanie, go for it.
Okay, I'm not muted yet, but yes, we do see the same thing, and in many cases, we're seeing some of these movements of these different groups, particularly fish, are much faster than we see with movement of, say, animals on land or migration of different species on land with this warming towards the poles. So we do see that. We do see changes. Again, mainly with these mobile species moving quite quickly. With the benthic species, the species that are attached to the bottom of the ocean, we see those movements slower. We see components of those systems moving. In fact, we see some corals showing up in northern parts of Florida and Georgia, or in Japan, much further north, and we've seen them for thousands of years. And so they are responding to the warming. The problem is they're not bringing the whole ecosystem with them. So a few corals are moving, but sometimes you don't have, it takes so much longer for the corals to build the geologic structure that supports all these other animals, that you've got sort of what we call a pulling apart of these ecosystems. But yes, I think we see it's a really great question that this person posed, because I think we are seeing exactly the same things in the ocean, and maybe we're not observing them as well as we can on land, but it's definitely seeing these kind of changes. With reefs, we're seeing not as many changes, but we are seeing them shrinking. So we've lost a lot of our reefs already. Some people estimate up to 40%, sometimes 50%, and we're expecting to see another. They'll be reduced to something like less than 10% of their original extent within the next 20, 30 years. So we're expecting big changes. It's just how do we keep these things intact during these big super changes that we're going to see due to warming and acidification. Diane.
That was perfect. The only thing I'll add to that is that this is one of the questions that the Biosphere 2 Ocean team is hoping to tackle. So one of our collaborators, Adriana Burgess in Australia, has been really coining this field with a number of others of what's called tropicalization. So what happens, as Joanie is saying, where some of these tropical fish species are moving poleward, and temperate and tropical species are interacting for the first time. So I think there's a lot of really, really exciting and challenging questions about what happens when these really novel ecosystems start developing that we've never seen before. And we think that the Biosphere 2 is a great place to test some of those questions.
And they might not be the only ones that are migrating soon. We have the issue of sea level rise that might start to intrude on some of our communities around the world. Joellen, could you talk a little bit about that? You're muted, Joellen.
Inundation is a huge problem, epic, in fact. And about half of it is, and I'm using this loosely, is due to the expansion of seawater just from the warming. And all the climate models include this, right? In all these are coupled ocean atmosphere simulations. They include the fact that it's warming and they have a dynamic height that allows it to rise. So you can actually see this. The problem is the models don't, and I'm gonna just flat say this, in the newest IPCC that hasn't even come out yet assessment, and including the one in 2013 that did, no scenarios include the meltwater from Greenland and Antarctica. Now, personally, in my lab, we've already done some of these simulations where we include this, and it changes global climate. Changes the sea surface temperature, it changes the sea ice, it changes the position of the tropical rain belt. It actually shoves it to the north side of the equator slightly, which does potentially change the rain here in Tucson. I'm not even joking. This is quite serious. And none of the models actually include it. Zero. So we have a MIP, a model intercomparison project that my group, or I, am running in conjunction with FAFMICH, which is run by Jonathan Gregory, which is a flux anomaly forced model intercomparison project where flux anomaly, we got the idea here. They do other things, but what I asked them was, what happens if we add all this meltwater from Antarctica? And we did it, and it is quite scary, but I'll just point out that in the climate models, all the glaciers, all the ice sheets, everything covering Antarctica are painted white rocks. There is no ice. You can snow on it and melt the snow, but the ice itself is static. And we know that that is nuts. Of course, it is gushing out of Antarctica and Greenland. These are very serious. And it just shows you, as climate scientists and as the taxpayer and public that are supporting us and doing this work, we are locked arms. We are in a race here, and so it's wonderful. I mean, I haven't talked to Joanie in years, but it's like I just saw her yesterday, because we are working alone together in the same direction, right? It's like a round dance works that way too. Alone, together, in the same direction. And we have got to bend this curve, and quickly, because I'm just saying the next thing we're going to do is add all that fresh water to the model. It's going to be big.
Thank you. I want to move towards coral bleaching. And this is a photo of Diane and her lab coring into a coral. to look at patterns of the past. And Joanie, you mentioned earlier that we didn't necessarily see a lot of coral bleaching before, 50 to 60 years ago. Now, was that because we weren't looking for it, or was that because this kind of thing has never happened until now? And maybe Diane and Joanie can pitch in on the historical context of these types of stress events. How do they, what does it look like when they've occurred in the past? People in marine sciences use the saying that it's taken 1 million years to build the coral reefs and this short amount of time to destroy them. What did that 1 million years look like? And was there die-off? And was there, renewal within that time span? Diane, why don't we start with you, because this is you, I believe, in the photo.
Yeah, I'd be happy. So the bottom line is, as your quote really nicely summarized, is that there have, of course, been times of change in the past. And when we core through coral, this is actually one of the examples of a fossil coral. So this coral was dead when we sampled it. We can take a sample through these living and fossil corals, and we can see evidence of stress in the past. So this evidence can be changes in growth rate. So like I said before, corals grow a lot like trees, and so they place down these annual bands that we can really clearly see in the skeleton. And so we can study sort of how that growth is changing through time. And one researcher in particular, Janice Loff in Australia, has really pioneered this work. And her lab and a number of other groups have put together a number of colonies like this all over the world. And we can see patterns of change when we put them together, of changes in growth rate as warming and acidification has happened. And so as we talked about earlier, one of the challenges is not that events haven't happened in the past, but it's the pacing at which these events is happening and the rates of change and the ability of corals to sort of acclimate or adapt to these changes. Our oceans haven't been static in the past. And so the question is how this current change compares to what we've seen in the past. And the bottom line is, in most cases, that it's unprecedented in a number of ways. And that's really the role of paleoclimate, is to put our recent changes in that broader context. And that's sort of the bottom line of what we've learned.
And I completely agree with what Diane has said, because this paleo evidence gives us such a insight into how fast these things can adapt to the current rate of temperature change. And so, to bring what she just described from the paleo record and how quickly or how slowly these changes have occurred compared to what we're doing today, that's the issue. We know corals can adapt because we've seen that happen in the past. We know that many organisms can adapt to these climatic changes that we've seen in the past, but the issue is how fast it is. And so today, that rate is like 10 times faster today than what we've seen, say, at the last time we had a big event, climate change event, called the Paleocene-Eocene thermal maximum, which was about 55 million years ago. And we saw big changes during that time, and that was 1/10 the rate of change that we're seeing today. So that sort of plays into, when I first started working on coral reefs, if we saw bleaching, it was a very isolated local event, usually because a lot of freshwater runoff or just a local temperature change that was just something that, like a spike that we would expect, to happen under normal circumstances every, few decades. But now we're seeing these global changes. And that's the problem with reefs, is that it's the global phenomena that are happening. And now it's not just during these El Nino events, it's happening almost every year. And we just had a lot of coral bleaching on the Great Barrier Reef. It's not an El Nino year. So, that is a consequence of the background warming that's occurring because of climate change. And that's why when we use these models, thanks to the very good modeling efforts of people like Joellen and people that I work with and people all over the world with these nice climate models, we can use those to say how fast is the ocean warming, how fast can corals adapt. And so right now we know that the natural rate of adaptation of corals just cannot keep up with the rate of temperature warming. And so we expect that by 20 to 30 years, we're going to lose most of our coral reefs. So the key, as Diane mentioned, is how can we help them adapt? And I think the next panel is going to talk a lot about that, about how we can speed up the adaptation rate of the corals. And I know you're doing that in Biosphere too.
Yeah, we are. And there was a question about supercorals and coral adaptability. I think we'll save that for the next discussion. But we also got a question from an anonymous attendee. They said, we can measure the increase and decrease rates of carbon emissions. Do we know yet how those rates impact ocean acidification? In other words, do we know how long it takes for ocean acidification to decrease after carbon emissions significantly decrease? So what is that response time? And maybe Joellen could start.
This is why robot floats. I've been measuring pH by hand, spectrophotometric pH measurements made from ship, since the 90s. It is really important and didn't used to be the way people thought, let's just straight measure the carbon. But I wanted to measure the pH because from the pH, we can learn a lot of things. And it is one of the factors that actually affects our ecosystems as well. This ocean acidification, I just want to point out that in the models, the first thing that you can detect change in that is not regional or an anomaly is pH. And you see it in 2 years. All it takes is 2 seasonal cycles because everywhere in the ocean, the pH is going down in this lovely seasonal cycle. And by the time you get to the 2nd year, you can tell that that is no longer, it is out of an envelope of reasonable variability just from sloshing around. And that's because the same effect, we see this massive atmospheric increase. David Keeling started at Scripps. He was one of my professors when I was at Scripps. I remember sitting down at the lunch table. All the other lunch tables were full, and he was sitting all by himself. And I'm like, he's an old guy with white hair. I don't know. And then I was just like, whatever, I'm going to sit down. I need to eat my lunch. I sat down, and he said, hey, who are you? And I said, I'm an oceanographer and I'm going to work on carbon in the ocean and it's going to be awesome. And he said, he was the nicest man. I do a little carbon work myself. And this is the guy who's the CO2 curve that he made is on the wall, carved into the wall at the National Academy of Science. And extraordinary. He started in 1958 in the South Pole and at Mauna Loa in Hawaii at just to get a clean air samples, right? And clean air samples and up and up and up they went. Now we have this global network that's telling us up and up and up they went. You can follow them on Twitter. You can actually follow his record as it grows. They actually send you a tweet a day to tell you what the CO2 is. I follow it because the CO2 goes up and the pH goes down. There are things that make it go down faster, like when we have an upwelling event of deep ocean carbon, which happens more often now that the winds have gotten more intense and fully crazy, particularly in the Southern Ocean. But yes, pH is felt, the increase in the CO2 in the atmosphere is felt immediately. And within 2 years, you can scientifically say that that is caused by the increase in the atmosphere. Faster even than you can tell the heat. And I did want to just say about the heat, basically the shortwave radiation from the sun comes directly in and warms the water at the surface. Shortwave radiation just is absorbed. When it goes to re-radiate it back out, what interferes with that is water vapor mostly and CO2, right? With how much long wave goes out. So the ocean keeps warming because we keep putting more CO2 in the atmosphere. So when you look at ERBE, Earth Radiation Budget Experiment, ERBE's my bud, it's my favorite experiment other than SOCOM. ERBE is basically a series of satellites, looks out of the sun and in at the Earth. And ERBE tells us that every single year now, that the imbalance, the difference between what's coming in, which is roughly the same every year, and what's going out, which is less every year, is a direct consequence of the fact that the CO2 goes up and the amount that gets out goes down. And where is that imbalance? It's in the ocean, because 78% of your surface is ocean, and as it mixes, it can actually take up even more heat from the atmosphere just through sensible heat transfer. So yeah, 92%, and it's directly warmed because sun comes in like every day, but it doesn't go out like every day. It goes out less because we have more CO2 just straight up now. And it used to be that we saw big peaks with El Niños and stuff, and now the top of the atmosphere is, Dan's like, it's not this straight line. And the atmosphere is not this straight line, because it actually is the tail and the ocean is the dog. And so the tail sometimes gets wagged by the dog, which is the ocean. But the Earth as a system, it's just up now. So we all need to bend that curve. We need to bend that curve. It's got to do it. Bend that curve. Sorry. Let me get that.
We did have a question from the audience, from Terry on Facebook. What are you doing to limit your CO2 emissions? And how can we as a society limit our emissions and make change in our oceans?
Such good questions. So me personally, I ride a Vespa. You know, that's how I get to work, right? We have a car. We try to minimize the amount of time, and it is a low, high mileage vehicle, not actually electric, but we have to be able to afford that. And double pane windows, more insulation. We reduce the footprint for our home. We have a Nest thermometer that we program to actually try and get more of those green leaves. It's a big deal. We're also trying to eat more veggies and less meat, but and more chicken than red meat. You know, there are all kinds of things you can kind of slide down the scale. We try to use less plastic, but that's kind of plastic's made out of hydrocarbons. So, it's another way to it doesn't really change your footprint, but it's important too. So we do a lot of things. And then big things is we try to vote and write to our Congress folk, because we'd like them to, and to our rate commissioner, et cetera, because we'd like them to help us move to greener power. Arizona's really lucky because we have a nuclear power plant that provides 40% of our electricity, and it's carbon free and it's paid for. Woohoo! We also have hydropower, solar power, wind power. And what we need to do is bear down on reducing the rest of the fossil fuel portfolio so that we then have cleaner skies, less asthma, better air quality, fewer deaths from COVID, one hopes, with better air quality. It's supposed to go together. There's so many benefits, and we live in this amazing state and would like to see it prosper. And yeah, everyone else can please feel free to copy us. Wouldn't it be great?
We are starting to close in on time here, so I might give Joanie and Diane one last round. And Joanie, we certainly don't have enough time to hear about some of your coral reef nursery work, but any last kind of afterthoughts from the context of corals as we move into our next discussion?
Well, you are moving into another discussion, and I hope people tune into that one well, because that's going to be a lot of hope, I think, about what we can do with coral reef restoration. But what my experience in working with it has been amazing in terms of giving people hope. It's a really powerful emotion to just let people know that we're trying to understand the system. Our plan is not that we can save all the coral reefs this way, and you'll hear more about this later, but you give people, it's a reality check. I've been talking about climate change for years, and people really tune out to that. They don't want to hear about it. But when you talk about when you're doing a solution to climate change, whether it's restoring an ecosystem or whether you're working on something else, they will ask you about climate change. So it's a kind of a very psychological shift that I've noticed with people. When you're working on solutions, then they want to help you. If you're working on the problem and trying to describe the problem, they're not so interested. So that's kind of a big lesson, and I bet that comes out in the next session too.
Yeah. Well, thank you guys so much for joining us today and celebrating World Oceans Day. I think the three of you are you know, pioneers in these fields, and you're carrying the knowledge forward. So it's a real treat to be able to visit together, and it's nice to reunite Joellen and Joanie after a while, it sounds like, and you know, it's just a real treat. So thank you to everybody who joined us. We're going to be moving into our next session on coral reef resilience. So log out of this one and log into the next panel. We're getting tons of thank yous from our participants to the three of you. Great questions. We had one person say, "Go robot floats." So it's just good vibes coming from the audience today. And thank you guys so much. Happy World Oceans Day.
Happy World Oceans Day. Bye-bye.